So in the last video, we talked slowly through the process of computing properties and marginals, so like expectations, marginals, correlations for two variables given their contingency table. So I'm going to go very fast through a calculation for a different contingency table. So if you're confused, I would watch the other video and then watch this afterward. So this is like a speedier version. So we have x, y. X can take on 0, 1, and probability 0 for all others. Y takes on 4, 5, 6, probability 0 for all others. And this is a contingency table, right? So, boom, let's compute the marginals. So 1/6 plus 1/4 plus 1 over 12. So this is 2 over 24. This is times 6, 6, and this is 4. So this is 12 over 24. So that's 1/2. And since this is 1/2, this has to be 1/2. And then this is 1/3, which is doubling this, 1/2, and 1/6. So just summing these, summing these, summing these, summing these, summing these, right? So we have the marginals. Okay, now we have the marginals. Now we can compute. So first thing, are these independent, right? So let's check for 1/3, 1/2 is 1/6. 1/2, 1/2 is 1/4. 1/6, 1/2 is 1/12. 1/3, 1/2 is 1/6. 1/2, 1/2, 1/4. 1/6, 1/2, 1/12. Good, they're independent. So independent. So these are independent. Are they identically distributed? Well, no, because y takes on values with non-zero probability. So let's just take an example. Probability y equals 4 equals 1/3. The probability x equals 4 is 0. I mean, it's not even listed in the contingency table because all of the values for which the probability x taking on the value 0 are not listed. So clearly, these are not. If you did out the probability mass functions, they would not look the same. Y would look like this. Y would be here. And x would look something like this, 0, 1, and you'd have probabilities here, right? So these would be different heights, and these would be the same height. So this would be y, this would be x. So these would clearly not be the same. So they're not identically distributed. They're not identically distributed, right? Okay, so let's compute the expectations. So the expectation over x is 1/2 times 0 plus 1/2 times 1 equals 1/2. Expectation over y. So notice, like last time, we were able to compute the expectation over y as the same as the expectation over x because they're identically distributed. In this case, they're not, so we have to compute it again. We have to do a separate calculation. So this is 1/3 times 4 plus 5 over 2. This is not going to be fun. Okay, plus 1, right? So this is 8 plus 15 plus 6 over 6, which equals 29 over 6. So that's kind of not a nice number, but yeah. Okay, so we have the expectation over x, expectation over y. Let's compute xy. So this is going to be a bit of a feast. So first thing let's compute x times y for each of these combinations. So the nice thing is this is all zeros. So 0, 0, 0. So in the summation, we can just disregard these terms. That's good. And over here, this is 1 times each of these, so that's just 4. 1 times 4, 1 times 5 is 5, 1 times 6 is just 6. So we just have 4 over, I'll write it out. So 1/6 times 4, notice these are all zeros, as we said. 1/6 times 4 plus 1/4 times 5 plus 1/12 times 6. So let's make it 12. So this is 8 plus 15 plus 6 over 12. Okay, so that's again 29. Really? I guess. Yeah, 21, 20, 29 over 12. Okay, that's convenient. So let's compute. So we have 29 over 12. Let's compute variance. So to compute the variance, we can first compute e of x squared and e of y squared. So e of x squared is going to be 0. So it's 1/2 times 1 squared. So it's just 1/2. E of y squared is, okay, this is going to be 1/3 times 4 squared plus 1/2 times 5 squared plus 1/6 times 6 squared, right? 1/2 5 squared plus 1/6 times 6 squared. Okay, so this is not so much fun. So this is 2 times, so 1632 plus 3 times 75 plus 36 divided by 6. So that's 7. 143. That's right. So that's e of y squared, and now we can compute the variances. Variance of x squared, variance of x. This is 1/2 minus 1/2 squared, right? So e of x squared minus this squared. So that's 1/2 minus 1/2 squared equals 1 over 4. Variance of y is going to be some b's. So this is e of y squared minus e of y squared. So this is going to be 143 over 6 minus 29 over 6 squared. Whatever this beast is. Okay, so now we have, the variances, we have e of xy, we have expectations. So we can start calculating we can calculate the covariance and then the correlation. So the covariance, it's the same calculation. So covariance x, y is going to be this minus this times this, right? Let's write it out. X, y, e of x, e of y. So this is 12 minus 1/2 times this. So e of x times e of y. So 1/2 times 29 over 6. 9 over 6. Right? And this is, I wrote it out. This is 12. That's convenient. Wow, that's really convenient. Okay. 29. Yeah. Right. So, oh wait, that should be the case because yeah. So the covariance comes out to 0. So that's interesting to note here. So the covariance, so the slope of the line relating x and y is 0. So it's just going to coast along, right? So what does that mean? Well, and why is that the case? Well, if they're independent, if there's no relationship between them, then you clearly cannot describe that relationship with a line. So the best line you can get is a flat line. If this were 0, that doesn't mean there's not some other relationship. But because there's no relationship, because we showed these are independent, that means that must be the case, right? So this coming out to 0 is not surprising. And because this is 0, the correlation over x and y, we didn't actually need to compute these variances. I guess we shouldn't have, but the correlation over x and y is going to be 0 divided by the standard deviations, which is just 0. So we don't need to deal with these variances. If we did, we would take 0, whatever. If this were not 0, we'd take whatever this were, divided by the square root of this times the square root of, where did we have this? 1/4. The square root of 1/4. We erased it, but we had that the variance of x. Oh, right here. Right. The variance of x is 1/4. So the square root of this times the square root of this. That'd be the denominator here. Yeah. So that's it. very fast version of these problems.